Hi and welcome back to the Electronics channel. I'm going to continue now discussing the series on charge balancing circuits. So what I want to actually do today is work out how we're going to characterize a typical charge balancing circuit, in particular the sort of active inductive balancer type circuits like I looked at in the previous part. What characteristic does it give us in terms of current flow between the cells with various voltage differences and so forth. So we can look at the ways that we can characterize that and how we might expect it to look when we do that. So let's go back to the fundamentals and say, right, we have two cells. What would be the easiest way to balance them? Well, if they were independent, then we could simply connect them in parallel. That would force the voltage on each cell to be the same, and because we're doing voltage balancing here, that means effectively we're going to automatically balance the cells. They're connected in parallel. Some current's going to flow, don't know which direction it's going to flow in, depends on which cell has the higher charge initially, and that current's going to keep flowing and it's going to decay away until the charge is equally balanced between the cells. So in terms of profile of current against time, if we define our current as I in this direction for the time being, it's going to start out at some value. Let's say cell 1 here, V1, was higher in charge to start with. Then we'd start out with a positive current. It would decay away quickly, or fairly quickly, and it would drop down to almost zero levels as time went by. So if V1 had more charge in it, then the current would flow in that direction to redistribute the charge between the cells. So these would self-balance just by virtue of the fact they're connected in parallel, which is great. The only thing limiting the current in this case is the resistance in the wires and the resistance in the cells themselves. So the cells would have some kind of internal resistance, which is not a fixed value. It's not like a real resistor. It does vary depending on charge state and temperature and all those other things. So it's kind of a variable resistance depending on the conditions, but nonetheless it is a way of limiting the current. It does affect the current flow. So we've got these three elements which determine what our peak current's going to be when we just connect cells together like this, which by the way you should probably never do unless you know those cells are pretty balanced to start with. You could get some pretty high currents flowing, so it's not advisable to do that. So what will the characteristic be here for this kind of simple charge balancing circuit, which let's say we had an external resistor which we were putting between the cells to make it more safe? What would the characteristic of that balancing circuit look like? So if we plotted, let's say this cell is V2, this cell is V1 in terms of voltage. If we plotted V1 minus V2, so the difference in cell voltages, where V1 if positive puts us in this on this side of the chart, then I would flow in that direction. So with I, define that, we'd be in this quadrant up here. So if V1 is greater than V2, that I would be positive. Charge would be going from cell 1 round to cell 2. So we'd have something in this quadrant. And because this is a simple resistive balancer, then the characteristic would just be a straight line, like this, where the slope of that line is given by the value of resistance. If the resistance is lower, then this line would be steeper, the current would be higher for any given voltage difference, and obviously if the resistance is higher it would be more shallow, and because it's completely bidirectional this curve would just go through zero on both sides. So if cell 2 was the higher potential, V2 higher than V1, would be over this side of the curve, the current would be in the other direction, so we'd be in this quadrant, and it would have exactly the same characteristic. It would just be that of a resistor. So that's fairly simple. I think that's relatively easy to understand, but of course in reality we can't balance cells like this. We don't tend to want to take our packs apart, rearrange them so all the cells are in parallel, and then when we want to use them rearrange them all back into series again. So of course what we're more interested in is the active balancers that you can get nowadays. So we have our more standard series pack of cells, and we put our active balance circuit. I'm going to stick with two cells for this analysis because it just keeps things easy. We connect to the common point in the middle, So we've got 3 wires going into our balance circuit here. And then we've got a cell with V1, cell with voltage V2. We're going to define our currents like we did in the previous video. So I1 is going to go in this direction. In fact, I think I called it I plus before, but I'm going to call it I1 this time to keep the 1 nomenclature common. And I2 is actually going to be actually, I'm going to, for simplicity this time, actually, I'm going to define it the other way around, because although it made sense in the last video, for this one, I want, if the voltage coming out is if the current is coming out of the cell, I want a positive value for the current. So in this case, if the current's coming out of the cell, it's actually going to be going in this direction, out of the positive, and out of the positive that way. So I'm going to define I2 as this direction on this video. So I know that might be a little bit confusing comparing between the two, but it makes drawing this graph make a lot more sense. So anyway, we have 2 cells connected to our balancing circuit. This balancing circuit is going to analyse the difference in voltage between cell 1 and cell 2. So if cell 1 has a higher potential than cell 2, then the balance circuit is going to draw current out of V1, so I1 will be positive in that case. Say V1 with a higher potential, I1 will be positive, and it's going to be putting current into V2 to redistribute that charge. So the current I2 is actually going to be negative, as I've just defined it here. And interestingly, these 2 currents do not have to be the same, because this is not a simple resistor. There's not just one current as there would be in this simple parallel case. We've got this connection in the middle which can carry current as well. So we're not talking about I1 and I2 being the same thing. So interestingly, we're going to end up with 2 characteristic curves for this circuit. One looking at it from I1's perspective and one looking at it from I2's perspective. Now there's also a third current, of course, here, which is this middle one here, which, depending on how we define this, is either I1 plus I2 or I1 minus I2. So we've got this current IB, which I think previously I've defined it in this direction. So going into that junction there. So IB in this case is I1 minus I2. So this equation is true for this circuit. You know, IB is equal to I1 minus I2. So it might be interesting to also see what the plot looks like in terms of against IB as well. So for this we'd have the same thing on the x-axis. We'd have V1 minus V2. So again, that's the difference in cell voltages. But on here we could plot I1, or we could plot I2, or we could plot IB. And I think, you know, I1 and I2 I'd expect to be reasonably similar, because if this thing was 100% efficient, then, and the cell voltage are, you know, they're not going to be that far apart. But on those 2 assumptions, cell voltage is similar, 100% efficient charge redistribution, and these currents would actually be very similar. Of course, if one cell is considerably different voltage to the other, that won't be the case. So yeah, it's going to be interesting to see what plotting the different currents gives us on here. Now, what shape would we expect with an active balancing circuit? Well, that depends on how the circuit works, of course. We know a little bit about the ETA 3000, which is the balance balance charge balancing chip we talked about in the first video. And we know that if the cell voltage differential is below a certain threshold, so that would place us, you know, somewhere in a region on this line like this, so the voltage difference is too low for the chip to operate, then the current's going to be 0. So we can draw a line there like that, and then when the voltage differential gets above a certain threshold, the chip fires up into action. So we're going to start to get a current flow. Now, in terms of I1, we've already said if V1 is greater than V2, that puts us on this end of the line. We'd expect I1 to be positive in that case, because charge will be drawn out of cell 1. So we're going to be in this quadrant. So it's going to either suddenly jump up to some value, so let's say it was starting at 0, a bit like a resistive balancer here. The current might jump up to some value, then it would probably ramp up in some way some characteristic that's sort of proportional to the voltage difference is what you'd expect. So it would have some kind of resistive characteristic, but it may not be truly linear because this is a switch mode device at the end of the day. You know, it can transfer energy with quite high efficiency. So this may not be a simple straight line curve. Then at some point it's going to reach its current limit. It has a maximum current that it can charge balance with. So we may expect the line to flatten out as the current limits itself. So we might end up with something like that for I1. And in this case, because V1 is greater than V2 and I1 is positive, V1 is the source cell, if you like, and because we're plotting I1, this is the source part of the curve. Now if V2 is higher than V1, but we continue to plot I1, then the current's going to flow in the opposite direction because charge is going to be taken out of cell 2, it's going to be redistributed into cell 1, which means I1 would be negative. So we're going to be in this quadrant down here. V2 greater than V1 puts us over here, I1 now negative puts us down here. But this curve may look a little bit different because we're now in the quadrant where this cell is not a source anymore, it's a sink. So we're now in the sink part of the characteristic, but as I said before, we speculate it's going to be pretty similar because the voltages on the two cells are, going to be reasonably similar. So the whole thing may be scaled slightly from one side to the other, maybe slightly different scales, but it's going to have a similar kind of characteristic with the current limit, again, limits how much current is being put back into that cell. So that's the kind of curve we might expect to see with an inductive charge balancer. Of course, now we also have on eBay these capacitive charge balancers. So instead of using an inductor to store energy and then transfer that charge over, you charge a capacitor up from one cell that's got a higher potential, and then presumably, I don't know if this is how they work, but I'm assuming the case, connect that capacitor that's now charged to V1's voltage that's higher, you then connect it to V2, which has got a lower voltage, so current will flow from the capacitor into that cell until the two equalise, and then you repeat that cycle repeatedly. So you charge transfer using a capacitor as the storage element. They may have a completely different characteristic. So it would be interesting to try and measure this characteristic for the inductive type balancer and then compare that to the capacitive balancer and see how they look. The capacitive balancers seem to have a higher current capability in general, so we may find that this curve, this characteristic curve, has a higher slope. So for a given voltage differential we get more current, so more strong balancing. Again, we may see that they have a current limit on the capacitive ones, but some of the literature I've read suggests that they don't. It may just keep on going. So presumably there's some point at which you can break these capacitive charge balancers. If the voltage differential on your cells is too great, or one of the cells gets short-circuited, maybe, the current could become very high in theory. So again, it'd be interesting to see what the characteristic for the capacitive type balancers is, and compared to the inductive ones, which we know have a current limit because of the semiconductors used in the chip. So the question is, how are we going to try and measure this characteristic? So I've been thinking about this a little bit, and I've got one plan. We could use obviously the cells, so we could just take a pair of cells and we could deliberately mismatch them. So we either apply a load to one of them to discharge it, and then we get a voltage differential, and then we can measure the currents. But that's all happening in real time, so you have to be measuring the currents in real time as the cell discharges. So I was thinking maybe there's a better way of doing this. Could we make one of the cell's voltages fixed? Well, the answer is yes. We could substitute that cell with a power supply. So if we take a DC power supply, that represents one cell in our balancing scenario. So here's our balancer, like that. So we can have a power supply which can only supply positive current because it's a power supply, it doesn't sink current. So again, V1 and I1, so it can only supply positive current. So we're only going to measure one quadrant having the power supply in that position. On this side we're going to expect the current to be in this direction as well, because we want charge to be transferred into this. So if this was a cell, I'm going to draw it as a load at the moment, I'll just draw it as a resistor. If this was a cell, we'd expect the current to be going in this direction, into the positive side, charging that cell up. So taking charge out of this cell by having current coming out of the positive terminal. On this cell we want the current going into the positive terminal to transfer the charge. So if this circuit powers up in this state, we put a resistive load on there to simulate the lower cell, then we get a current flow in this direction. We get a voltage drop on this resistor, and we could measure some kind of characteristic curve that way. So we'd be transferring energy from a power supply up here in this position to a resistive load down in this position. So this may work, but it may be a little bit difficult to control because the current through here is going to be dependent on the voltage difference, but we're not really controlling the voltage down here. It's just a resistor, so the voltage is directly proportional to the current. So depending on what current ends up flowing, gives us our voltage, which then gives us our voltage differential, which may determine our current. So this may not be a stable way of measuring the characteristic. So my idea was, what about if we replace this with an electronic load? So we get rid of this as a resistor, we connect some kind of black box here, which is an electronic load, and then we can control the voltage quite precisely because we can tell the electronic load to say keep the potential at, let's say, 3.8 volts and just draw whatever current you need to hold that potential at that level. So that should be a much more stable scenario, much more like a real battery cell, because it's difficult on a real battery to change its potential quickly because you need a lot of current to change it quickly. So here, if we've got an electronic device which is keeping the potential fixed, this circuit should be a lot happier, I think, doing that. So my plan is, in the next part of this series of videos, is to try connecting up the charge balancing circuits with a power supply and electronic load in this configuration, and then measuring I1, I2 and IB, obviously V1 and V2 as well, and plotting those characteristic curves and see what we get. Now, because these are switching elements, I don't know if the current through these connections is going to be absolutely smooth. We know this is an inductive balancer, so the current is going to be chopped, as we saw in the previous video. So if you remember this sketch from the previous video, we saw that I plus and I minus potentially have this very choppy waveform where they go from 0 to this ramping current and back again. So I think I'm going to have to probably add some capacitors in here just to take out the ripple and smooth things out for the power supply and the electronic load. So effectively get it back into a nice smooth DC. So any choppy currents on this side become smoother on this side. So we may need to add some capacitors on there, but obviously with standard capacitors they're not like batteries in the sense that they take a while to charge, they don't hold a lot of energy, they're purely there to remove the ripple. They don't pass any DC current because they're capacitors, so I think they're not going to affect our transfer function measurement at all. So I think that's okay to do, and indeed there will be capacitors on board this circuit anyway already for this purpose, so I don't think there's any harm in adding those on there. But yeah, I think this is going to be very interesting to try. I may need to persuade this circuit to wake up by actually having a power supply on this half as well to start it up, so we may need to have another one here so that we can get the scenario where it looks like two batteries are connected and they both have potentials on them, and then when we start the test we disconnect the second power supply. Once current is being dumped into the electronic load, we can just turn that off, plot our characteristic, and off we go. It's going to be interesting to see if we can make it work, but I think this is going to give us the data we need, and it's going to allow us to compare the different types of charge balancing circuits that we can get our hands on. At the moment I have the ETA 3000 based inductive charge balancer to try, and I also have bought one of the capacitive charge balancing circuits. They're both for 3 cells, but I think I should be able to persuade them to work with just 2 cells, which is the scenario we're sort of emulating here. So it's going to be interesting to get some results from that. So in the next part of this video series, I'm going to be setting that up on the bench, seeing if I can get it to work. Fingers crossed, if it all works out, we'll start plotting these curves against the different currents. We should, in theory, be able to calculate from these curves the current. Obviously, the current versus the voltage differential is what we're plotting. We should be able to work out the efficiency as well by comparing the energy being drawn out of cell 1, let's say, compared to the energy being dumped into cell 2. So we can see what losses are being generated by the charge balancing circuit by analysing the two sets of power readings that we can get from the measurements we're taking here. So we should be able to extract the efficiency curve, the current versus voltage difference curve, and get a good feel for actually how good these charge balancing circuits are. So yeah, I'll see you in part 3 of this video series, where we get this wired up on the bench and see what happens.